of a web tool named Visual KARSYS that is dedicated to 3D geological modeling and especially in link with heterogeneous aquifers. And this presentation will be done by Arnauld Malard from ISSKA in Switzerland. So hello Arnauld, thank you to be with us today.
Good afternoon, everyone.
A few words to present you before you start your presentation. So Arnauld is an hydrogeological. He has an hydrogeological background, especially on karstic and volcanic context. He has been working for ISSKA, that is the Swiss Institute of Speleology and Karst Studies, for now 12 years, I think. And since 2016, he has been in charge of the developments of Visual KARSYS. That is the scope of his presentation today. So Arnauld, please, the floor is yours now.
Okay, thank you, Philippe. So, okay, welcome to everyone. I will share my screen. So Philippe said me that we have almost 30 minutes of presentation, and I will show you different slides, and also I will show you the web tool directly, and so we have time after that for discussion. Okay, so let's start. I will share my presentations first. Okay, so today I will try.
Just Arnauld, to let you know, it seems that your camera is muted, so we cannot see you for now.
Yes, but
okay, now it's okay. And I presume your presentation is coming.
Yeah.
Perfect, we can see it.
Perfect, you can see it. Okay. Okay, so let's go. So yeah. My talk calls Visual KARSYS, and so Visual KARSYS is a web tool basically for modeling karst aquifers in 3D. So you can see at the bottom of my screen, so there are many different logos. They refer to all institutions and organizations. They support the work of the ISSKA for developing Visual KARSYS. So all along the past years, I will say, so many of these different services and institutions, they provide us a kind of support, like financial support or institutional support to develop Visual KARSYS. So, and I would like also to thank all of them, because I know that some of them are also in the room today. So then, thank you. Okay, let's start. So as said by Philippe, so I work at the Swiss Institute for Speleology and Karst Studies. So just, okay, Philippe already said a few words about this. So we are like a competence center on karst and caves. So basically the idea of ISSKA is to improve the management of this specific environment. So from a geological point of view, environmental point of view, biological point of view, and so far. So we are a non-profit organization. We work here in La Chaux-de-Fonds in Switzerland since 2000, and so we are from public utility. We are almost 13 employees here, and our activities is around consulting, research, development, teaching, and also some advice for authorities. And we also have a large network of collaboration in Europe, but also abroad. Okay, the background of Visual KARSYS started now, I will say something like 10 years ago. I will say at the end of a research project which called Swiss Karst, and which was funded by the Swiss National Fund. And in the frame of this 4 years project, so we developed a conceptual approach which called KARSYS in order to model karst aquifers in 3D explicitly, and in order to provide, I will say, most of the informations that are useful for the stakeholders, engineers, so people, they need different informations to solve their issues they have with the karst. So based on this KARSYS approach, so we published different papers, PhD theses, guidelines, and so far. And we had different people coming from different countries, from France, from China, from Ireland. So they were all speaking about KARSYS, and they all want to try KARSYS, want to apply KARSYS on their own site. And so it was quite nice and quite, I would say, enthusiastic for us, of course. But the problem was that at that time we did not have any tool or any support for the people to apply KARSYS by themselves, just guidelines and a few scripts and so nothing else. So, and that was in 2016. So we opted for developing a real web tool online that allowed the people to apply KARSYS by themselves. Okay, so then in 2016 we started with some money provided by the Swiss Federal Office for the Environment, plus many different cantons also, and some other private partners that provide us financial support. And we start developing a web tool here at ISSKA, but also in collaboration with the high school of what we call the Northwestern Switzerland, and also for some different aspects with BRGM. And so in parallel of this development also, we also push a lot of, we'll say, weight or pressure on the marketing, on the courses, on the conference, on the networking in order to to develop Visual KARSYS and to make Visual KARSYS available for all of you, basically. Okay, Visual KARSYS today, since 2019, it's on production, so then anyone can use Visual KARSYS and can work with Visual KARSYS. So it addresses two types of user. From one side, the modelers, so people, most of them, say, people that are geologists or hydrogeologists, they produce a geological model or hydrogeological model. They work from private companies or in different scientific organizations. And on the other side, so it also addresses what we call the end users, so mainly the people from administrations or public authorities. They need documents, information on Karst, but they are not really interested by the tricks of doing geological models or by producing geological models by themselves. Okay, but they need this information to apply their regulations or to face the issues they have with Karst. And in the middle we have ISSKA, which is continuously developing and supporting the users with Visual KARSYS. And since 2019, so it's online, but we'll still have different extensions and development. So you will see. Okay, today, so these are the last stats, I get it. So we almost have something like 1,250 users on Visual KARSYS. So it's about 20 to 30 new users per month. It's quite cool. And okay, and so now how does it work? Visual KARSYS, if you'd like to discover it. So you go to visualkarsys.com and you just create your account in My Visual KARSYS. So then you just put your username and your password, and you will enter in Visual KARSYS as a modeler. So when you enter as a modeler, so you arrive on what we call a community page, where you may have already some project that have been shared to you by some colleagues, for instance, or project which have been put public by some other users also, because they are of public interest. From this page, basically, you can create your project by giving a name, description, and when you create a project, you enter into the editing part of Visual KARSYS. So then you have a wizard here, which have been first made for hydrogeological interpretation in Karst. So, but all along this wizard, you will see that we will do different things from the data integration, geological modeling, and so. So the first thing we have to do, as usual, I will say, is to define the project and also to put the data into the soft. So then basically we define the coordinate system, we define the extension, and based on that, we can already integrate the digital elevation model, the different geological maps, the different geological cross-sections we have by knowing also the coordinates of the extremities of the cross-sections, the respective elevation for each cross-section, also different boreholes and some other, I would say, underground works like galleries, like pipes, like mines. So where we can get geological information, basically. And we arrange all this information in 3D, in a real 3D scene, where you can check by yourself how the information are consistent, if they are well located at the right scale, at the right dimension. So this is really what we call the setup at that step. So you're not supposed to do any kind of interpretation, just put in your data and just see if your data fits with, I will say, all together, basically, and already in space. Step number 2 is to define what we call the geological series and the geological units. I will not enter into the detail, but if you are, I will say, used with GeoModeler, for instance, or Leapfrog or so, it's more or less the same way. So then you have to define different series, and in all these series you can have different units with their name, with their respective color, and also with different properties. So here basically it's about hydraulic and hydrological properties, permeability, hydraulic conductivity, and so. And you can order this series and unit from the chronological order of deposit. Based on this, you will enter into the geological module of Visual KARSYS, and this is probably the module or the part of Visual KARSYS which is the most interesting for you. So this is the part where the user, they are supposed to really build their geological 3D model, starting from the cross-section, the maps, the drill holes, and based on the hydrostratigraphy they defined. Okay, so in this part, so you will retrieve the different cross-sections, the different maps, and on this you will pick what we call the contact data between the different units directly on the cross-section. Like you do in GeoModeler, for instance, it's more or less the same manner to do. And you will also pick some tip information, so where you're supposed to give the orientation, the inclination also. And you can also draw at different places some faults that cross the different geological units. Okay, so you do that on the cross sections, on the different maps you have, but you can also draw the same or pick the same geological data on the drill hole, and then already ask Visual KARSYS to run the geological model just close to your drill hole to see if the geological data you enter fit with the environment, I will say, around the drill hole. Okay, when you have already entered the different geological unit and you are, I will say, happy with the number of data and the amount of data you have, so you can ask Visual KARSYS to create directly or to build directly the geological mesh in 3D. So then you have different resolutions that are available, but you can also customize your own resolution along the 3 different axes in the space, so along X, Y, Z. So then each time you have also an indication of the time, the computation, the expected computation times it will take for a small project of low resolution. It could take a few seconds, but for a large project with a high resolution, could take up to 3 hours, something like this. It depends on many different aspects and features of the geological model. And okay, so and then after a few seconds, minutes, or hours, so then you get your geological model in 3D and directly online. And and you can just check it. And if you're not agree, you can go back and change the geological data, add more geological data, and so forth. For the next step, step 4 and step 5. So basically, these are steps we used for the hydrogeology. So then basically, this is the steps that are dedicated to the interpretation of the 3D groundwater zone and of the groundwater flows. So then basically we enter the springs. I will not enter into the details here because we're mostly here to speak about geology. But basically you can enter the different springs and then based on the springs, so we can already provide a first assessment or first estimate of the main flooded zone in the different in the different geological unit of the model. So everything in 3D, of course, and so then you can appreciate by yourself, okay, where I'm supposed to have the main big flooded zone in my geological model. And so then step number 5 is the step where the user can also enter some additional information regarding dye tracing tests, regarding flow paths, catchment of the different springs and so. And so in order to add some documentation on the geological model. After that, when you completely different 4 to 5 steps, so basically the job as hydrogeologist is done. So then we move to the end users because we complete all the different steps for the completion of the geological model and the hydrogeological model. So then we just change from the modelers to the end users, and we access Visual KARSYS by what we call the end user page or the output page, where the end users, they're able to see and to get all the details of the project and of the geological model, the data, and also the output. And so the output page, of course, is online. So then you have a 2D map as well as a 3D SAM, where you can check all the time, okay, what you have in 2D and what does it refer in 3D. So of course you can change background maps. You can plot the 3D geological layers as a 2D map with the ISO lines, so that you know exactly on different location of the space, okay, at which depth you can cross these specific layers of marls or limestone or so. You can create cross sections everywhere in the perimeter of the project, and then get a picture of the cross section. You can plot also the groundwater zone, and you can add some custom sketches for any kind of different things. You can also export the data from the output page, the different data. You can print the maps, you can print the cross sections. So then basically the end users, you just as geologists and hydrogeologists, you just provide the geological model, the hydrogeological model, and the end user, they can get all the information they want at the place they want, in the format they want, so by themselves. They do not ask you, okay, can you prepare me a cross section from this point to this point, because I have a meeting in 1 hour, so then I need one. So then they can make it by themselves. And for this, of course, you need to give some permissions and to share the project from users to users. So then basically this is a big strength with Visual KARSYS, that you can create your project and decide who will benefit from your project and which kind of access they could have also, like the contributor. The contributor, they can also work on the geological model, they can modify the data, they can update the geological model, or just the viewer permissions, where the people can just access the data and the output, and they cannot modify anything. Okay, about the demo directly. So I think you still see my screen with Visual KARSYS because I changed. I hope it's okay. I hope it's the case. Okay, so then I just open a project in Visual KARSYS. You can see here, this is the page where the project is summarized. When we enter into the setup of the project, you can see this is the digital elevation model with the maps. You can see the different cross sections here that have been extracted from literature and put in 3D at the right place and more or less at the right scale. So you can access all the data at any time. You can edit the data, the coordinate, the elevation. There is a drill hole also here in the middle, so somewhere here, which is called test. So then you can see you can also create some drill holes, and you have also the possibility to define some underground galleries, mines, or pipes. So I mean tunnels. So where you may have some geological informations to help you to build the geological model. Okay, so then it's really, I will say it's really free. It's really intuitive the way you can use it, because you have the different cameras, the vertical exaggeration here. Basically, you can also have the different view of the different layers. You can select a cross section and start to isolate the cross section, for instance. So basically, you can do a lot of different things. I will not enter into the details, but that's what you can do. The hydrostratigraphy part is the part where you will define your series and define your geological units. You can reorder the different geological units. You can group them, split them in another series, and so far. So basically, you can play. It's really flexible. You can play with the different series. You can edit them, change the color, and okay, it's really quite intuitive also again. And now we arrived into the geological part. So everything is saved also. That's also the strength of the online, of the web service, that everything is saved on the servers. We don't have to save by yourself the different things. And you just select the sections you entered before. So for instance, I will, try this one. And you can see the place which is concerned by the geological model. And so maybe it's not so clear on that one, but I will. Okay, let's go. Take this one, for instance. You can see here the different geological data which have been put at the top. Here we work on top, at the top of the geological units. So then basically here's the top of the Mars, the top of some calcareous limestone, calcareous Mars, top of the Mars here also. And you can also give the dip, and you can see the dip refer to the Argovian Mars with an orientation of 150 and a dip of 66. So basically, it's quite easy to pick the data, because you have, if your cross section are well dimensioned and well located in the space, so really you have just to pick the data at the right place. So if I go to one cross sections where I do not have any data, so let's say this one, I can already ask Visual KARSYS based on the other data. I can ask Visual KARSYS to compute directly the feedback of the geological model, which is extrapolated from the other data at the exact place, at the exact place of this cross section. And I can, by using this cursor, I can really, I can compare what are the result of the geological model compared to the original data, and I can find the best fit with the zoom or with the transparency, and then I can say, okay, for instance, so the yellow unit is not really the same shape that the one I observed in my cross section. So then you can decide to modify by yourself by just here in the select box. You just get the top of the unit you want. For instance, here I need to modify the top of the limestone. So then I will get the contact data and then just put some additional data at the top of the limestone, like here. And now I can also ask Visual KARSYS. It will be a bit different. I can ask Visual KARSYS to just take this new data into consideration to modify the geological model and to plot a new cross section at that place by considering this new data. So then you can see here that morphology of the yellow deposit has been adapted based on the data you just put. So, and then that's the way you have to work with Visual KARSYS. You really work with the cross sections, with the maps, with the drill holes, and at any time you can really pick your own data, remove your data, and adapt your data compared to what is compared to the output provided by the geological model. So we can switch also, just for you to know, to the drill hole. So for instance, here I have a drill hole. So then I know that, for instance, I wrote this just a few minutes ago. I know that, for instance, the marls here, the Argovian marls here, are located between a depth of -350, or let's say from here to -450, like here. I just select the position for the top and the base of the marls. I apply, and then I can also ask Visual KARSYS to compute a geological model, just an extraction of the geological model in 3D with all the data, but close to the drill hole, by taking also into consideration the data from the drill hole. So, and you can see here, if we zoom and if we deselect different unit, so you can see here the drill hole, the marl, the Argovian marls that are here, from here to, let's say to the bottom of the drill hole, which has been modeled by Visual KARSYS close to the place where they're supposed to be. You can, of course, add many different drill holes, and you work the same way for all the drill holes, and also you work the same way with the galleries. Based on that, I will so you can build your entire meshes, the geological model. So I will, just to save time, I will keep the low resolution, which is about 155,000 points. So it will take about 15 seconds to compute. But if I ask for a medium resolution of 8 million points, it will take 8 minutes, something like this. And if I ask for a high resolution of more than 125 million points, it will take more than 2 hours. So then it's an expectation. Of course, in reality, it's different, but it could take time. Let's keep the low resolution. I compute the mesh to the low resolution, and you just count something like 15 seconds in your mind, and after that you will get a real 3D mesh of this entire geological model. So I will just select the cross sections for you to see that the aspect is a bit shiny today. So there is obviously a problem with the light, but basically this is the geological model that you can get, and you can also make all the unit transparent or deselect the geological unit, and so you can play with the geological model as you want. Okay, let's go to the output page. So we now enter as the end user into this project. So basically, as I said, you have many different functionalities that you can do by yourself. You can also explore the 3D model with all the commands related to the 3D models, but you can also observe the 2D map, and by using the commands related to the 2D maps, like a GIS. But more than GIS, you can create your own cross sections where you want. You can also create some virtual drill holes at the place you want. You can change the background maps. You can create some isoline maps of the geological layers. So let's say we'll select the top, for instance, the top of the Argovian marls. Just select the color and save. And then Visual KARSYS will compute the top of the Argovian marls and plot it on the map. So like this, you have a map based on your geological model of the top of the Argovian marls. Go back to the slice. So the slice have been computed, the cross-section have been computed, as well as the virtual drill hole. So now I can ask Visual KARSYS to display the cross-section directly. So then I click here, just have to wait a few seconds for the cross-section also to be prepared. And then you can get here a real cross-section that you can also explore because it's interactive. You can pan, so then you know exactly at which elevation you are, in which unit you are for which elevations, you know the name of the faults, you know different things, and you can recalculate the slice because it's based on the geological model. And you can export it. You can also do the same for the virtual drill hole. So let's say we have a virtual drill hole, so we can get also an extraction of the geological model along the vertical at the place where the drill hole has been put. So these are all the different things you can do as end users. You have a button here where you can export different data. You can export even the geological meshes directly in 3D if you want to use them directly in another soft. You can export the other data as shapefile, as XLS file, so as geology zone also, so many different formats. Okay, so this is for you to know, to see a few more examples of different geological models. So this is the geological model of high precision made in the city. So you can see was the digital elevation model included in the buildings. So then it's really a high scale or low scale. I never know geological model. So this is another geological model made in volcanic context. So you can see here the lava flow. So this model is about 45,000 million points. So it's quite a huge resolution. So then, of course, you can explore this geological units. So you can deselect the geological unit. You can do the same way you do with the other geological model. And I have also another example of a geological model here from the Jura region, so where you have the succession of folded and trusted geological unit. Okay, so it's really, you can, if I deselect the geological unit, I can also get the faults in 3D with different relations between faults, if they stop on some other, if they are just finite, infinite. So you can play with these parameters also. So this is for the demo, and now about the I will say the future of Visual KARSYS. We have already some extensions that have been made since 2019, like the GeoModeler import for a GeoModeler project, the dynamic flow animation module. I will just show you how it looks like. And we are working on some developments right now for what we call the meta project. I will show you, and Fraxis, which is a project related to the same conceptual modeling of hydrogeological modeling fractured aquifers. And we also have some perspectives of work by working on the GPU acceleration to accelerate the geological modeling, the computation of the geological model, and also to work with the BIM, building information models for civil engineers also. So these are all the things we can work on. With the extension of the flow animation module, the dynamic flow animation module, the constatation was that Visual KARSYS was nice, but it was too static. And so we then get some fundings from Danone in order to really work on a 3D animation module that you can set by yourself, and where you can set precipitation rate, you can set the ratio of evapotranspiration and so, and you can generate rainfall over the ground, and you can simulate the runoff, you can simulate the infiltration through the Purview's geological unit, as well as the runoff over the impermeable basement, and you can also simulate the flow within the phreatic zone, so the confined zone of the aquifer, which is full of water. This is the blue patch here, and also the water which flow out of the aquifer via or through the Karst spring, which is the sphere here at the back. And so this is the developments we are working on right now. It's still in beta version. If you're interested to play with, just ask me. It works. It's nice. And so it's everything online and in real time. There are no, I would say, no preliminary computation before. This is for the flow animation module. And And we also work on this meta project functionality, which allow the users to, this could be quite interesting for you. This allows the user to combine different geological model of different scales with different geological data in a child model. Even if they have different faults, even if they have different lithostratigraphy or lithologies in geological units. So we have to find, you have just to indicate a matrix between the geological unit from the parent model and the geological units of the child model, and also for the fault. And then you can synchronize or link the different geological 3D model and get one which is made from one or two other, or three or four, or I don't know how many other geological models. So, and then it works actually, but we're still stuck with the faults for just the question of preview. But really the idea is that you can make a geological model in place based on some other existing where you have the permission. Even if they have different scales, even if they have different geological units, you can extract the units you want, get or synchronize the units you want, synchronize the faults you want, and then get the child model. And after a few, I don't know, a certain time, if the user from the parent model, they decide to change or to add some data or to modify data in the parent model, they can, and you will be notified in the child model that the data has been updated or has been added or has been removed, and you will be notified if you want to accept or to reject this new data or this new modification. You can do this and then keep the link or just unlink with the parent model. So the idea behind this functionality is really to ensure the data traceability from the different model at different scales. It's also to allow the people, the user, to imbricate a geological model at different scales, like the Russian dolls, you know. So you have the small one in the middle one, in the big one, and also to overcome what we call the scale effects related to the geological models, and also the borders affecting between two adjacent geological models, because you can, in just one click, create the geological model at that place. I mean, at the border between two existing geological models. Okay, this is for the conclusion of Visual KARSYS. Okay, it was quite fast, I think, as presentation, but I think for the essential you get in mind. So this is an online 3D geological modeler, which is available for everyone because it's free of charge, and it will stay free of charge with additional functionalities also, which are toward the hydrogeology mainly. It's based on the geological, on the implicit 3D modeling, we'll say algorithm. And as I said, there are some extensions related to karst hydrogeology, but also to somewhat other heterogeneous media like volcanic or fissured or glacial aquifers also, basically based on this flow animation module where you can simulate the rainfall, the runoff, the filtration. Today is about more than 1,000 users. We also provide, or we also offer some courses during the year, and there are also today some courses that are inside the scholar courses at the universities. So, for instance, in Lyon, Neuchâtel, or Besançon, also they use Visual KARSYS as a teaching tool for the students. So we are still working on Visual KARSYS today with different developments and many different perspectives, but in parallel also we are always looking for finance because development's cool. Okay, it takes time also, it takes resources, and so as Visual KARSYS is free, we have to find some other ways to finance the developments we do. So if you're interested, you can just for the info, you can join the group in LinkedIn, visualkarsys.com, or you can just follow us on X, I will say the X Twitter, or to create an account in visualkarsys.com. So thank you for your attention.
Thank you.
That's the...
Yeah. Thank you very much, Arnauld, for the presentation and the demonstration. So it's time for questions and discussion. So if any, of course, you can raise your hand and ask directly Arnauld. Is there any question in the audience? I can start with one question regarding the slide you presented for the next functionalities and this parent child link you propose. I wonder how do you ensure the coherence between the models you combine in terms of geology? Is there a link via the geological pile or whatever?
Yes, in details, it's in details. In fact, you do not implicate directly the geological models, or you just implicate the geological data. So the idea is really to share the data from geological models to geological models. So then it's that, and then from the parents model, they have their own data. They are computed with the algorithm in a model, and the child model get the data from the parents model, and it's computed apart from the parents model. So then it's a new computation, but the data are the same behind. So then your question is how to rely between the parent, the consistency of the model between the parent and the child model, right?
Yeah, I understand that you are not combining or mixing the result, the models, but you are combining the data.
Yeah.
That were used to build the two different models in the example we can see here on the screen. But that means that these data have to be coherent in the sense of the geological pile you described earlier in your presentation. They need to fit the description of the geology that is an input for the geological model.
Yeah, exactly. So okay, so exactly. So you will. So basically, I will. Maybe if I do that, it will work. Okay, basically, you define a project where you know at the place where you know you have some other project. So then you select the project you want to combine or to link, basically. Based on that, okay, you can select the different cross-section maps you will add to your new child, but that's not the question you have. But the question you have is that how to combine the geological units from the child model with the parents model. So basically, this is made at that step where you have a match to do between the hydrostratigraphy. So then this is the hydrostratigraphy or the geological unit of your child model here, where you can see you have many more units than the one you have in the parent models. But now the idea is really to classify, to order the geological unit in this kind of matrix for all the parents model with the child model. And then in this way, you will only get the geological data from the parents model, which match the one you need for the child model. If, for instance, in the child model, which is a biggest model, you don't need to define the different units within the Jurassic, for instance. From the parents model, you will only keep the top of the Jurassic, and you will not keep exactly the different units you have inside the Jurassic. So then you will make a kind of sort or sorting of the different geological units from the parents model. You will link to your child model. Okay. Everything is made here in this correlation matrix for the geological unit, but also for the thrust, because you may have different faults. Maybe it's more clear here. You may have a fault here in the project, in the parent project, and which is fault B, and fault G in the other parent project, but in fact, in your child project, it is fault here. So then basically you have to combine data from these two faults by keeping these two faults like original in their home project. And in your child project, you will get the data from these two faults, but combined in a new fault. So that's really the idea. But every time we know, okay, fault here, basically it's fault B plus G, which are respectively in their parent project A and B, for instance. So then if you modify this fault in the parent A, so then you will be notified in the child project, okay, the fault R could be adapted because the fault B has been adapted in the parent project. That's the way you can also ensure the consistency between all the data, because everything is linked and you keep traceability from the child project to the parent project. It's a bit, yeah, it will take more time to, but the best way will be to use it.
Thank you for the explanation. So we have a couple of questions in the chat. So a question from Laure. If you want, Laure, you can unmute your microphone and ask directly to Arnauld.
Yes, I'm here. Yes, I was just curious about the model where you were showing some flow lava structure, and I thought it was very well handled. So I just have a question about how many control points you have, because you have a kind of anisotropy of the structure, and sometimes it's very difficult to handle with this kind of implicit method. So if you have any advice on how to do this kind of model.
Yes, yes, good question. So yes, of course, it's quite, I mean, building geological model in this volcanic area is quite different from the one you can build in, I will say, in sedimentary context, where everything is more or less on lap or just scattered by fault. So in this context, so you have to define of all the units you have, like just eroding or erode unit or erode series basically. And I think if I remember well, I think I just define 1 unit per series. Yes, I define 1 unit per series, and each series you can see is erode series. So then basically, by this way, it's quite, I would say it's not easy, but it's more simple to handle with this configuration of each unit being an independent series and an erode one. And after that, I think there are not a lot of control points in this project. I think it's just about 360 control point in this project, which is, not remember, but it's a large, it's quite a large project because it's more than 8 kilometers by 5 kilometers. So it's not so many contact data, but so the number of contact data is not really important. So what is really important is the place where you put this contact data,
of course,
which is more important than the number of contact data. So there are really key places where you have to put the exact right data at the right place to really well model this place. And so sometimes I try to also work with less data because it's more easier to know exactly what you do, and also because it takes less time for computation, basically.
Yes, of course. Thank you.
We also have a question from Mayuri. Mayuri, if you want to unmute your microphone and ask directly, please do so.
Yeah, hi. I have a question. If Visual KARSYS can be also used to model lithology of an area which would have a non-karst aquifer. Just for context, I work in an area with very less subsurface information. So we have a few groundwater monitoring wells and a few resistivity profiles, but nothing beyond that. So I'm wondering if the software can be used.
Yes, thank you for the question. Yeah, of course, so basically it's really a question of background. So we started to we developed this geological modeling tool because we needed to apply KARSYS. But basically, the first focus for us was the Karst aquifers. But once we developed this, so we observed that okay, extensions or applications could be more large or larger than just Karst aquifers. Of course, the project you see here is not in Karst, is in the volcanic aquifer, and we have also some other projects which are not in Karst, but in some other heterogeneous fields or environments. Yes, you can. Basically, for the geological model, it doesn't change anything. You can build geological model from everywhere. So basically, for the step 4 and step 5 of Visual KARSYS, it's much more restricted to Karst, or at least to a high permeable lithologies, basically, like in volcanics, or for instance. But yes, the idea was to start with something. We started with Karst, and so it's not restricted to Karst, but it's much more focused on Karst actually. But for the geological model, you can build geological model from everywhere.
Yep. We also have, it's not really a question, but maybe more a comment from Cyrilda in the chat, requesting or asking from more lecture or workshops about this kind of topics. So this is certainly something to consider in the scope of the EGS for the next future. We still have some time before 3 o'clock. If you have any other question, once again, feel free. I have another one for you, Arnauld, regarding. So you said that the use of Visual KARSYS is via the web is free of charge. Can you say something or some words about the link with an open source approach? I understand it's not maybe really the case in what you are developing.
Yes, yes, Visual KARSYS. Then the use of Visual KARSYS is like Facebook. It is free of charge, but you don't have access to the code behind. So because why? So because we started like this, and also because there are a few functionalities in Visual KARSYS which are actually not released for everyone. So some of them because just the maturity of the functionality is not still okay for being in production for everyone. And also the other reason is also because we try also to keep certain functionality just for us. Yeah, just for us. But okay, but basically it's free. There will be more and more functionalities for free, but there will be also more and more functionalities that will be also restricted to certain users. And regarding the open source of the code, that's something that can change also in the future, because at the beginning we started like this because it was also a quite a small risk for ISSKA to invest a lot of money in this development in an open source code, because we're a small institute without a lot of resources, and I was a bit afraid from the big enterprise or companies that can take this code and probably also offer the same service than me, but okay, but they're just bigger than me, and so they can have much more resources and much more. So that's why I restricted the use of the code at the beginning. But now, as we are okay, we are now in production. It's something we can decide to change later.
Okay. Any other comments or questions before concluding this webinar? There is a comment or an answer from Pierre-Yves Jeannin to the question from Mayuri. You can read it on the chat. So I see no raised hand or no more questions in the chat. So I think we can conclude now this webinar. Thank you again, Arnauld, for your presentation today.
Thank you also for your attention.
And and thank you to all of you for your participation and watching. So it's time to close this webinar.